Hi everyone, good morning. Morning classes are actually good once we wake up. Waking up is little bit hard, but after that morning classes are nice. We can keep our uh, after the syllabus completion, we will have this revision classes, practice classes. So those classes we can keep in the morning, you know, just to have all the students in the discipline. Okay. Anyway, we will see that. Hi everyone. Is the audio, is the volume now fine, Arpan? Okay, so I will keep the mic closer. Now, let's see now. So after the syllabus completion for the 4 months, remember in September, our syllabus will complete. And after that, October, November, December and January. So for 4 months, we will do practice, revision, practice, revision, practice, revision. Every day, we will have one class. Okay, 1 hour class, not much because students should study. We will have only 1 hour class every day. And in that class, we will do revision of one topic, only small topic we will take, and for that topic we will take a lot of questions. So basically practice plus revision, this will continue for 4 months. And also we will do test series discussion, you know and like everything that students need to know, we will do. Okay, so now let's focus on this lecture number 10 in graph theory, that is vertex cover, edge cover matching. These are the three concepts that we will study today. Okay, let's start now. In the last class, what we have seen, we have seen independent set. Independent set, that is set of vertices, right? Yes or no? Independent set, that is basically that is vertex independent set, means you have set of vertices which are independent. Independent means they are non-adjacent, means they don't have any edge between them. Okay, correct. So this is your vertex independent set, right? Yes or no? So we already know what is independence number. What is that? Can anyone tell me? Independence number. Independence number. This is the size of largest independent set. This is the size of largest independent set. Very simple. Okay. So we have already seen what is the what is a vertex independent set. This we have already seen. Basically, this is a set of vertices. Remember, this is a set of vertices which are independent. Okay, means they are non-adjacent. They don't have any edge between them. Correct. So this is the idea. Now tell me, in this graph, can you notice in this graph, this if you notice, this xy is this maximal independent set. This x comma y, like this one, this x comma y is this maximal independent set. Can you add something more? Can you add something more? No. You can notice x comma y, they are non-adjacent. They don't have any edge between them. So this x comma y, this is independent set because they are non-adjacent. They don't have any edge between them. But you cannot add anything more. I cannot add anything more. So this is maximal. This xy, this is maximal. And what about this? What is the maximum independent set? What is the alpha of this graph? So if you call this graph G, then what is alpha of this graph? Means independence number. What is alpha of G? In alpha of G, this is basically the independence number. This is the independence number. So what is the independence number? Or I can say stability number. What is the stability number? That basically means, okay, what is the largest independent set that you can create? Largest independent set very easily you can create. So you can take WUV. Okay, so you can take these vertices. You can take these vertices, WUV, correct? So basically the number will be 3. Okay, so largest independent set, if you notice, this will be the maximum independent set. This will be the maximum. Very simple. Okay, now let's move on. One more thing, you already know the star graph, right? Okay, so let's take the star graph. You know star graph. Star graph means k1 comma n. This is your star graph. For example, I can say this is the star graph, like A, then you have B, then you have C, then you have D, then you have E, and then you have F. So this is your star graph, and this is your vertex A. Tell me in this, can I say this is maximal independent set? Is this maximal independent set? Can I add something more? Yes, this is maximal. This is maximal independent set. I cannot add something more. And what is maximum? And what is the alpha of this graph? What is the independence number of this graph? Alpha of G. Alpha of G. What is the independence number of this graph? That will be 5. Because what is the largest? What is the maximum independent set? Maximum independent set. So the largest independent set that you can create, that will be B, C, D, E, F. This is the largest that you can create. Very simple. Okay. So like this, you already understand all these concepts. In this, what is the omega for this graph? What is the omega of this graph? Omega of this graph, that is your maximum click number. This is your maximum click number, correct? Very simple. Okay, because what is the largest complete subgraph you have? In this, what is the largest complete subgraph? So you can notice K2, K2, K2 is the largest complete subgraph, K2. Okay, so finally I can say omega of G, that will be 2. Largest complete subgraph, that will be K2. Okay, now the next concept is vertex cover, edge cover. The name itself is telling you vertex cover, vertex cover. Actually, there is some confusion here. Let me tell you. Okay, so you just give me a second. Okay, just give me a second. Yes. Okay. So what I'm saying, vertex cover, edge cover. So first, let's see what is this vertex cover. This vertex cover. The name itself is telling you vertex cover. Actually, what we cover here, what we cover, vertices or edges. See, the name is vertex cover, but what it means vertices which will cover edges. Okay, here actually we cover edges. Let me tell you, here we have vertices which cover all edges. Vertices which cover all edges, which cover all edges. They should cover all the edges. So remember, actually we are covering the edges. So okay, but we call it vertex cover because vertices which will cover all the edges. Let me explain this concept using this like using this scenario. So let's assume there is a museum. Okay, like for example, maybe okay, there is some museum. Okay, maybe like whatever. You have some I can say okay. So you have some hall, let's assume. Okay, so now in this hall, what you have? So for example, let's assume this type of situation you have in this hall. Okay, so let's assume this type of situation you have now. Okay, so this type of situation, some situation you have this like this type of hole is there. Okay, so like this type of situation you have. Now tell me one thing, tell me one thing. Actually, these are the galleries. Okay, like here you have paintings. Okay, like let's assume here you have this is a some I can say this is a painting museum. I can say this is a painting museum. Then in this painting museum, what you have? So you have, let's assume these are the galleries. Now, okay, now these are the galleries you can notice. Then tell me how many security guards you need. Actually, these are the galleries. So here, here you have paintings. Here you have paintings. Like on these walls, On these walls you have paintings. On these walls you have paintings. Okay. Then what we actually want, how many security guards will be there? Tell me how many security guards we need to cover all the paintings. Like we want to cover all the walls. We want to cover all the walls. All these walls we want to cover. Correct? Is this problem clear? So you have a painting museum. In this painting museum, how many security guards you need? So what is the very trivial answer? Can anyone give me very trivial answer? Anyone? Very trivial answer. 100 security guard. Yes or no? 100 security guard. Like one security guard you place everywhere. Yes or no? One here, 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 one here. Yes or no? This is a very trivial answer. Correct? Yes or no? Very simple. You don't have to apply your brain. But what is the interesting question? Tell me what is the interesting question? If I ask you, the interesting question is minimum number of security guard. Correct? Yes or no? So tell me, what is the minimum number of security guard that you need? Minimum number of security guard, such that they will cover all the walls. Minimum number of security guard. Okay. Tell me one thing. Okay, if you want to cover this, one security guard you need here. One security guard you need here. Now this security guard will cover this, and this complete. Okay, so this is covered. These walls are covered. Correct? This security guard can cover. Okay, if you put this security guard here, then this security guard can cover all these galleries. Next, one security guard you have to put here. Okay, what you can do, you can put one security guard here. This security guard will cover this gallery. Next, one security guard I can put here, and this security guard will cover all these. So how many minimum? How many you need? Minimum. So minimum we need 3. Yes or no? So I can say minimum size of vertex cover. Minimum size of vertex cover, that will be 3. Is this clear to everyone? So what is the vertex cover problem? This vertex cover problem is very simple, that you want to cover all the edges. Vertices which will cover all the edges. Remember, you have to cover all the edges. This is important. So you have to cover all the edges. Now, so let's see the terminology. If you have this graph, let me give you a graph A, B, C, D, okay, E. So let us assume this graph you have. Now in this graph, let's assume, tell me one thing. What are the edges that A will cover? Okay, this vertex A covers which edges? Covers which edges? This vertex A. Let's see which are the edges that are covered by vertices. So first, here I will write the vertex, and here I will write the edges covered. Here I will write edges covered. Okay, so what are the, tell me, if I have this vertex, so tell me, if I have this vertex, which edges will be covered? There will be 2 edges that will be covered. Okay, this AB edge will be covered and AC edge will be covered. You can clearly see, because this A is covering these edges. So AB and AC, these edges will be covered. Okay, what are the edges covered by C? C will cover which edges? C will cover this edge. Remember, AC and CA, they are same. Yes or no? Remember, this edge, this is just a convenience. I told you that this is just for convenience. This is just for convenience. This edge A, C, this we will write as AC, and this is same as CA. They are basically same. Okay, this is the writing convenience. This is for convenience. For convenience, this is what we will do. This I told you. Okay, remember this edge you have. So this is your edge A, C. This we will simply write as AC, or I can write it CA. Both are same. AC, CA, both are same. Okay, so this C, this will cover which edges? AC, CD. These edges will be covered by C. Which edges will be covered by B? This B will cover, AB edge will be covered, BE edge will be covered, BD edge will be covered. You can notice these edges are covered, and you can notice C will cover these edges. So like this you can say. And similarly, for finally I can say that, for example, E, what edges E will cover? E will cover, I can say E will cover BE edge and E will cover ED edge. So you can notice these 2 edges are covered by E. So this is simple. Okay, so this vertex, if you put a security guard here at this vertex, which edges will be covered? If you put the security guard here, then this and this edges will be covered. And if you put a security guard here, for example, if you put a security guard here, then this edge, this edge, this edge, these three edges will be covered by this security guard. Okay, so this is the idea. Now let's see the same thing I will do. If I put security guard on edges, what I do, I put security guard on edges, then which vertices are covered? If I put security guard on edges, for example, if I put a security guard on AB edge, then which vertices will be covered? One security guard I put here, one security guard I put here, then which vertices will be covered? Only A comma B, these vertices will be covered. If I put a security guard on ED edge, then only these vertices will be covered. Like if I put a security guard here, then this and this, these two vertices will be covered. And similarly, if I put a security guard at CD, then this C comma D, these will be covered. These vertices will be covered. So is this concept clear? So here you can notice, if I put security guard on vertices, then edges will be covered. So here vertices are covering edges, and here edges are covering vertices. Okay. So now what is vertex cover? What is vertex cover? Vertex cover means vertices will cover edges, and edge cover means edges will cover vertices. Okay, so this is the idea here. Vertices covering edges, vertices covering all edges. This is important. All edges must be covered. Okay, vertices covering all edges. And what is this edge cover? What is this edge cover? This is edges covering all vertices. Covering all vertices. Basically, tell me, in this scenario, where we put the security guard? Where we put the security guard in this scenario? For the edge cover. For the edge cover, the security guard we put at the edges. On the edges we put. Yes or no? Because edge cover means edges which cover all the vertices. So we will put the security guard on edges. Okay, so I can say that this is the idea. Vertices covering all the edges covering all the vertices. This is the simple idea. So here I can say the security guard. I can say the security guard. I can say where we put the security guard on vertices. We put security guard on vertices to cover edges, to cover all edges, to cover all edges. And the same scenario here we put the security guard. Okay, here we put the security guard on edges. This security guard we put on edges to cover all vertices. To cover all vertices. Is this concept clear to everyone? What is vertex cover and what is edge cover? So don't confuse. Vertex cover simply means that you are putting the security guard on vertices. You want to cover all the edges. Okay. Edge cover means you are putting the security guard on edges. You are putting the security guard on edges. So you want to cover all the vertices. So this is the very simple point. Now, in both these scenario, what is interesting problem? For example, if I give you this A, B, C, D, okay, this graph I give you E, then tell me, is this interesting problem? Maximum vertex cover. Is this interesting problem? Tell me. Maximum vertex cover. Maximum vertex cover. Is this interesting problem? Maximum vertex cover. This is not interesting problem, because what will be your answer? There you don't even have to apply your brain. See, you don't even have to apply your brain. So this is not interesting problem. This maximum vertex cover is not an interesting problem, because you can simply do this. And is this interesting? Maximum edge cover. Maximum edge cover. Is this interesting? No. What you will do? Again, the same thing you will do. You will put the security guard everywhere. You will put the security guard everywhere. So of course, this is not an interesting problem. These two are definitely not interesting. These two are definitely trivial. These two are definitely trivial and not interesting. They are definitely not interesting, because what you are going to do, you will just put like here maximum edge cover. So what you will do, you will put security guard on all the edges, and here you will put security guard on all the vertices. So these are basically trivial and not interesting. So what is interesting? So what is interesting? The interesting problem. What is the interesting problem? That is the minimum. The interesting problem is basically the minimum vertex cover and minimum edge cover. This will be the interesting problem. Yes or no? So this minimum vertex cover and minimum edge cover, these are the interesting problems. These two. So finally, what is the minimum vertex cover? Minimum how many vertices I need? Minimum how many vertices I need to cover all the edges? I want to cover all the edges. I want to cover all the edges. See, I can put one security guard here. I can put one security guard here. So now these three edges are covered. These three edges are covered, and I can take B comma C. Yes or no? Yes or no? This is the minimum vertex cover. You cannot cover all the edges by a single vertex. So this is the minimum vertex cover. And what about this minimum edge cover? In this minimum edge cover, we want to cover all the vertices we want to cover. So if you want to cover, for example, if you want to cover this, we want to cover all the vertices we want to cover. So for example, tell me, to cover this vertex, what is mandatory? I want to cover all the vertices by edges. What is mandatory? This BE edge is mandatory. This is mandatory. Yes or no? This edge we have to take. This is mandatory because to cover this vertex, we definitely have to take this edge. Next, what we should do? So now these two vertices are covered. These two vertices are done. Now we have to cover these three vertices. These two vertices we have done. So see, B comma E, these two vertices we have covered. Now I can take A comma C. These two vertices are done. One vertex is remaining. One vertex is remaining. So now you can notice all the vertices are covered. Now you can notice all the vertices are covered. So the minimum edge cover that has size 3 and minimum vertex cover that has size 2. Is this clear? The concept of vertex cover, edge cover. In vertex cover, we find set of vertices which will cover all the edges. In edge cover, we find set of edges which will cover all the vertices. You can notice this will cover B comma E. This will cover A comma C. This will cover B comma D. So now you can notice all the vertices we have covered. Every vertex has been covered, and here every edge has been covered. So this is the minimum vertex cover and this is the minimum edge cover. Is this concept clear? Let's take another question. For example, if you consider this C, A, B, D, E. Okay, this is your graph. Tell me which is a vertex cover. I want to find which are the vertex cover. So can I say this is a vertex cover? Tell me which is a vertex cover. Is this a vertex cover? Is this a vertex cover? I am not asking minimum or maximum. I am asking vertex cover. Is this vertex cover? No, this is not a vertex cover. This is not a vertex cover. Okay, next, tell me A comma D. Is this vertex cover? This is not vertex cover because it will not cover all the edges. See A comma D. If you put one security guard here, one security guard here, then these two security guard cannot cover these two galleries. These two galleries cannot be covered. So this is not a vertex cover. So tell me, A, B, C, D, E. Is this vertex cover? Is this a vertex cover? Yes, this is a vertex cover because it will cover all the edges. It will cover all the edges. Every edge has been covered. Now tell me, is this a vertex cover? Is this a vertex cover? Yes, this is a vertex cover. And tell me, A comma B comma E comma D. Is this a vertex cover? Is this a vertex cover? Yes, this is also a vertex cover. Tell me one thing. Is this minimal? Is this minimal? Is this minimal? Can I say this is minimal? This is not minimal. Why this is not minimal? See, for example, if one security guard is here, 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 are they minimal? Are they minimal? No, you can remove something. Yes or no? They are not minimal. You can remove something. For example, you can remove C. You can remove this C. So this is not minimal, I can say. What about this? Is this minimal? Is this minimal? Can you remove something? Can you remove something? Is this minimal? Can you remove something? From this, can you remove something? Yes, this is minimal, right? You cannot remove something. We cannot remove anything. This is minimal. And this is also minimal, and this is minimum. This is minimum. Yes or no? Is this clear to everyone? The concept of vertex cover. So remember, this is also a vertex cover. This is also a vertex cover because it will cover all the edges. This will also cover all the edges. This will also cover all the edges. You can notice this is not minimal because you can remove C. You can remove C. You don't need C. This security guard you don't need. This is not minimal. You cannot remove anything. And this is minimal, also minimum. This is minimal also and minimum also. Okay, you cannot remove anything, and this is the minimum. Now the same thing can we do for edge cover. What can you say about the edge cover? Which of the following is the edge cover? Like for example, can I say this CB? Is this the edge cover? This C comma B, sorry, this CB, this edge CB, is this the edge cover? This is not the edge cover. Which edge, which vertices this is covering? This is covering only C comma B. Only C comma B. These two vertices are covered, but the remaining vertices are not covered. Okay. Now, next, tell me one thing. What do you think? Minimum how many edges we need to cover all the vertices? Minimum how many edges we need? Remember, one edge will cover how many vertices? One edge will cover how many vertices? One edge will cover only two vertices. For example, I can take CB. This CB will cover C comma B. These two are covered. So now C comma B are covered. Now I can take AC. Now these two are covered. Now what is remaining? What is remaining? So CB, AC. I have to take CD to cover this, and I have to take EC. So actually this is the edge cover. Yes or no? This will be the edge cover. Actually, this is minimum also. This is minimum also. This is minimum edge cover. Is this clear? Okay. The concept. Tell me, this is interesting thing. One edge will cover how many vertices? One edge can cover how many vertices? One edge covers exactly two vertices, right? One edge covers exactly two vertices. One edge will cover exactly two vertices, not more than one, not not more than two, not less than two. One edge will cover, okay, because if you have this edge, for example, this edge you have where you have U comma V, then this edge, if you notice, this edge E, I can say E covers U comma V. These two vertices, this E will cover. And what about vertex? What about vertex? One vertex can cover how many edges? One vertex can cover how many edges? Can cover any number of edges. Can cover any number of edges. Can cover any number of edges. Okay, remember, one vertex can cover any number of edges. There is no limitation. One vertex can cover any number of edges. For example, here you can notice this C, A, B, D, E. Here you can notice this C is covering all the edges. This vertex C covers all edges. Here, all the edges are covered by this vertex C. And here you can notice this C, A, B, D. Here this C is covering how many edges? Here this C is covering how many edges? C covers only one edge. Here C covers only one edge. Okay. So basically, this is the idea. And what about this graph? Like A, B, C, D. Okay, what about this? This is your graph. Then tell me, D covers how many edges? D covers no edge. D covers no edge. Okay, this D will not cover any edge. So tell me, for this graph, what will the vertex cover? Vertex cover means vertices which will cover all the edges, which will cover all the edges in this. So you can notice this will be your minimum vertex cover. This will be your vertex cover. A, B, C, this will be your vertex cover. And A, B, C, D, this also will be your vertex cover. Which is minimum? You can notice this is minimum. You can notice this minimum. Is this minimal? Is this minimal? Is this minimal? This is not minimal because you can remove something. And this is also not minimal. This is also not minimal. So this is the minimum vertex cover. Okay, yes or no? And D does not cover any edges. Okay, for this graph, if you have this same graph, you have A, B, C, D. And tell me, what is the edge cover? For this graph, what is the edge cover? What is the edge cover of this graph? The edge cover, like edges which will cover all the vertices. Edges which will cover all the vertices. Edges which will cover all the vertices. Is it possible? Tell me, is it possible? Edges which will cover all the vertices. Okay, so this is the node. So let's take this is the node. So basically does not exist. I can say does not exist because you cannot cover all the vertices. Okay, edges which will cover all the vertices. You cannot cover all the vertices using edges. Yes or no? So this is the node. Edge cover exists. Edge cover exists. When? Tell me. If and only if. If and only if. When? Edge cover exists if and only if no isolated vertex. If and only if no isolated vertex. No isolated vertex. If and only if no isolated vertex. Arthat, minimum degree should be greater than 0. This minimum degree should be greater than 0. For example, take this graph A, B, C, D, E. For this graph G, you can notice that minimum degree is greater than 0. Now, what is the edge cover of this graph? Can anyone tell me the edge cover of this graph? Edge cover. Okay, so I can say this D, comma A, comma B, comma C. This is the edge cover. Is this minimal? Is this minimal? This is not minimal. This is not minimal because you can remove C. You can remove C. This is not minimal. So what is the minimal edge cover? This D, comma A, comma B. This is minimum. This is minimum. Or you can take A, E, comma A, comma C. This is also minimum. So many edge covers you can create. Yes or no? So remember, edge cover will exist. Edge cover will exist if and only if no isolated vertex. Is this clear to everyone? In which situation edge cover will exist? Oh, sorry. Sorry. Okay. Wait. So this vertex cover is fine. Okay, yeah. Sorry, edge cover. Edge cover. Edge cover means edges. So this will be your edge cover, A, comma B. So actually, this will be your edge cover, D, comma A. Okay, edge cover will be A, comma B, B, comma edge cover. What will be the edge cover? I can say A, comma B, B, comma C, A, comma C. This is minimal. Can I say this is minimal? This edge cover. Can I say this is minimal? Can I say this is minimal? This edge cover. This is not minimal. This is not minimal. So give me a minimum edge cover. So this is not minimal. Give me the minimum edge cover. So DE, AB. Now you can notice these vertices are covered. Only one vertex is remaining. Only one vertex is remaining. Now all the vertices are covered. So this is the minimum edge cover. I can also say DE. I can take A. I can take BC. I can take BC and AC. Okay, now you can notice all are covered. All the vertices are covered. This is correct. Okay. So is this clear? So I made a mistake. Edge cover means edges, which will cover all the vertices. Edge cover. So you can notice this is not minimal. This is not minimal. These are the minimum edge covers. These two are the minimum edge cover. Okay. Next, tell me, are the red vertices vertex cover? These red vertices, are they vertex cover? These red vertices, are they vertex cover? The answer is no, because this edge is not covered. This edge is not covered. This edge is not covered. So I can say this is not a vertex cover. What is the minimum vertex cover here? What is the size of minimum vertex, like minimum vertex cover? MVC. MVC means minimum vertex cover. Minimum vertex cover. Okay. And remember, size of minimum vertex cover. What we call it? Size of minimum vertex cover. Size of minimum vertex cover. We call it vertex cover number. We call it vertex covering number. Size of minimum vertex cover. Remember, this is called vertex covering number, and we denote by symbol beta. This beta symbol we use for vertex covering number. And the same thing we can do for edge cover. So what is minimum edge cover? This is your minimum edge cover. Okay. And what is the size of minimum edge cover? The size of minimum edge cover. Minimum edge cover. That is edge covering number. That is your edge covering number. The size of minimum edge cover. And the symbol for this The symbol for this is basically beta dash. Beta dash means this is beta. So here the symbol is actually beta dash. Okay, is this clear? Minimum edge cover. So tell me here, you can notice what is the minimum vertex cover? Give me a minimum vertex cover. Give me a minimum vertex cover. So you can notice that. See, I want a minimum vertex cover. I can take 3. I can take 3. I can take these 3. Okay, if I take these 3, then these edges are gone. If I take these 3, then these edges are gone. These edges will be gone. Okay, these edges we have covered. Now these edges are gone. Now what we can do? Now what we can do? We can take this 2 will cover these edges. If I take 2, these edges will be covered. Or what I can do? I can take 5, 1. I can take 5, 1. All the edges will be covered. Yes or no? 1, 5, 3. They will cover all the edges. 1, 5, 3. So this 1 will cover these edges. This 5 will cover these edges, and 3 will cover these edges. So this is a minimum vertex cover. Can you do with only 2 vertices? Can you do with only 2 vertices? Only 2 vertices can you do? Only 2 vertices can you do? No, 2 vertices are not enough, because one of them we have to take. Yes or no? We have to take one of them. One of them we have to take. One of them we have to take, definitely. So 2 is not enough. So finally the vertex cover number, what is that? Like vertex cover number means beta. Beta is actually 3. Beta means vertex cover number. And what is the minimum edge cover? What is the minimum edge cover? So we have to take this edge. This 3, 7 edge we have to take. This 1, 4 edge we have to take. Now these are covered. 4 vertices have been covered. We have covered these vertices. We have covered these vertices. Now we can take 2, 5 and 5, 6. Now we can take these vertices. So the edge cover number means this beta dash. This beta dash will be 4. Okay, is this clear? So quite simple. What about this? What about this question? Is this the vertex cover? Is this the vertex cover? This is not the vertex cover. So again, the answer is no, because not covered. Because this is not covered. Okay, you can notice if this is your graph, this is a vertex cover or not? This one, this the vertex cover, like these 3 red vertices? Yes, this is a vertex cover. All the edges are covered, but this is the minimum vertex cover. This is your minimum vertex cover. So I can say beta is equal to 2. For this graph, the beta will be equal to 2. Okay. So very simple. These concepts are actually very simple. Just apply the definition. These concepts are very simple. We have already seen vertex cover number, edge cover number, edge cover, vertex cover. All these concepts we have seen. Okay. Now, so this is your vertex cover. Like here, you can notice what is the minimum vertex cover. Here, the minimum vertex cover will be this vertex. This vertex will be the minimum vertex cover. Okay. Here, what is the minimum vertex cover? What is the minimum vertex cover? Here, you can notice that these 2 vertices which will cover all the edges. Okay. So like this you can see all these examples. Okay, let's see this question. Can you try this question? Like, okay, so can you try this question? Let me remove the answer. Now try this question. For this graph, tell me what is the vertex cover, like minimum vertex cover. Give me minimum vertex cover for this graph. What is the minimum vertex cover? What is the minimum edge cover? What is the maximum independent set? What is the minimum vertex cover, minimum edge cover? What is the independent maximum, largest maximum independent set? Remember one thing, if I write MVC, what it means? It means minimum or maximum. It means minimum or maximum. It means minimum vertex cover, because we are only interested in minimum vertex cover. And if I write MIS, independent set, then what it means? Minimum or maximum? Minimum or maximum? Here it means maximum independent set, because when you study independent set, maximum is what we want. If I ask you what this means? This means maximum click. This means maximum click. Okay, this means maximum click, because okay. And tell me, if I write MEC, then what it will mean? If I write MEC, minimum or maximum, what this will mean, minimum or maximum? This will mean minimum. Because when you study edge cover, you want minimum. When you study vertex cover, you want minimum. When you study independent set, you want maximum. And when you study click, you want maximum. Correct? Is this clear to everyone? Because see, if I ask you minimum independent set, that is trivial. If I ask you minimum independent set, that is trivial, right? This is the minimum independent set. Minimum. So minimum is not interesting. Minimum independent set is not interesting. What is interesting? Maximum independent set is interesting. So here maximum independent set is interesting. Here maximum click is interesting. Okay, so let's see these questions. All these questions, let's answer them. So what will be the minimum vertex cover? I want a minimum vertex cover. What that will be? If I want minimum vertex cover, what that will be? 256. Okay. So 256, are they covering everything? Yes. 2,5, they will cover all these things. 2,5. Yes. 256. This seems very nice. Okay. Next. 57 is not covering everything. 57 is not covering everything. 57 is not covering this edge. 57 will not cover this edge. So this is minimum vertex cover. Okay. Next. So you cannot, this is your minimum vertex cover. Next, what is the edge cover? You want to cover all the edges. So I can take 6,7. Now these are done. 6,7 are gone. I can take 4,5. Now these are gone. 4,5 are gone. I can take 1,2. These are gone. So these vertices I have covered. Which vertex is remaining? Only vertex 3 is remaining. So 3,6. Now all the vertices we have covered. And what is the maximum independent set? Maximum independent set. Maximum independent set. I want independent set. So I can take this 7. I can take 3. I can take 7. I can take 3. See, this is a complete graph. So how many I can take from this? Tell me, from this, how many I can take? Only one I can take. From this, I can take only one. So I can take 7. I can take 3. Then I can take 1. Then I can take 4. So this is the maximum I can create. Yes or no? Very simple. So remember, this is your maximum independent set. And what is the maximum click? What is the maximum click? Maximum click. This will be the maximum complete subgraph. This is your maximum click. This is the maximum complete subgraph. So the maximum click, I can say omega is actually 4. Alpha is what? Alpha is also 4. So you cannot, this will give you alpha. Alpha will be 4. Omega is also 4. And what is beta? What is beta? This will give you beta. This will give you beta. Beta means vertex cover. So beta will be 3. And what is beta dash? Beta dash will be 4. Okay. Let's solve this question. What will be the answer? What is the size of, actually the question is asking size, then why the options are like this? Okay, anyway. So tell me, what is the size of minimum vertex cover? And the question is asking which of the following is a minimum vertex cover? Two questions you have. Which of the following is minimum vertex cover? And what is the size of minimum vertex cover? Size of minimum vertex cover, that means beta. What is your beta? So tell me. Which of the following? Identify one of the minimum vertex cover. Is this minimum? Just tell me, is this minimum? B, C, D, F, G, I, J, K. B, C, D, B, C, D means this B, C, D, F, G, I, J, K. Is this minimum? Can you remove something? First of all, tell me, is this covering everything? Is this covering all the edges? Are we covering all the edges? Just check. Are we covering all the edges? First you check this. Are we covering all the edges? Yes, all the edges we are covering. But can we remove something? Can we remove something? Is this minimum? Actually, this minimum? So in this graph, so you can notice the size here. Let's start with the minimum actually. Okay, see, always start with the minimum. What is the minimum size? Here you have from the options. Look at the options. This has size 8. This has size 8. And this has size 7. And this has size 8. And this has size 7. So always start with the minimum. Let's start with this 7. Is this a vertex cover? Is this a vertex cover? BCE, FGIJK, BCE. Okay, BCE. Next FGIJK. Next FG, FGIK, FGIK. Tell me, are all the edges covered? You can notice. See, one thing you see, one very interesting thing. Why I am writing these big circles? Why I am writing these big circles? Like why I am writing these big circles? Because it is telling me which edges are covered. It is telling me which edges are covered. Yes or no? In the GATE exam, if this question comes, these are telling me which edges are covered. These things are telling me which edges are covered. Okay. So that is the reason I am writing these big circles. So let's see this option. So for this option, you can notice these big things you can create B, C, E, F, because this will tell you which edges are covered. This will tell you which edges are covered. So are we covering all the edges? Did I leave any edge? Did we leave any edge? All the edges are covered. Yes, all the edges are covered. So this is definitely a vertex cover. This is definitely a vertex cover because all the edges are covered. Every edge we have covered. Yes, correct. You can notice these big circles. They will tell you that every edge is covered. Oh, DJ. Oh, DJ is not covered. So this is not a vertex cover. Okay. DJ is not covered. So this is definitely not a vertex cover because this this is not covered. What about this? Okay, so this is not covered. Now, after this, let's see the next one. Let's see the next option. The next option. So this option is gone now. Now this option is gone. Let's see the next option. That is this option. Let's check. Let's check this option. Let us check. So BD. So now let me check this option. So this option is basically B, then you have D, then you have F, then you have G, then you have H. Okay, next you have I, next you have K. Did we leave any edge? Tell me, are all the edges covered? Are all the edges covered? Like, did we leave any edge? Just check. Yes, this edge is leave. This edge is left. See, this edge is left. This edge is left. So this is also not vertex cover. This is also not vertex cover. So this is also out of the picture. This option is also out of the picture. Now two options are remaining to you. Now let's check this option number C. This option number C, let's check. Option number C means ABC, ABC, E, H, J, K, L, J, K, L. Are they covering all the edges? Again, this edge is not covered. Again, this edge is not covered. So this is also not a vertex cover because this edge is not covered. So this is also gone out of the picture. This has gone, this has gone. So finally, the answer should be this. The answer should be this one. This would be the answer. Okay, anyway, let's check whether this is the answer or not. So BCD, then you have F, then you have G, then you have I, J, K, then you have I, J, K. Did we cover all the edges? Now tell me. Now we are covering all the edges, right? Now, yes, we are covering all the edges. So you can notice the beta will be actually 8. For this question, This will be the beta. Minimum vertex cover will have size 8. Okay. Tell me one more question. This is interesting question. The maximum degree vertex. What can you say about this? The maximum degree vertex. Should this be in vertex cover? The maximum degree vertex must be in vertex cover. Must be in minimum vertex cover. What about this? True or false? True or false? The maximum degree vertex, the vertex which has maximum degree, is it okay? It should definitely be in the minimum vertex cover. This statement is clearly false. This statement is false. You can create example. See, you can easily create a counter example. You can easily create a counter example. No, star graph is not a counter example. In the star graph, maximum degree vertex will be the minimum, will be in the minimum vertex cover. But you can create a counter example like this. What you can do, you can create a counter example like this: B, C, D, and then you can do E, F, G. Now take this. Tell me, what is the maximum degree? Which vertex has maximum degree? This vertex has maximum degree. All the vertices like these are 2, 2, 1, 1, 1. So all vertices, this vertex has the maximum degree. But what is the minimum vertex cover? What is the minimum vertex cover? Tell me the minimum vertex cover. The minimum vertex cover will be BCD. This BCD will be the minimum vertex cover. This BCD. Yes or no? So maximum degree vertex must be in minimum vertex. Maximum degree vertex must be in minimum vertex cover. This is false. Is this clear to everyone? A star graph is not a counter example. Don't say that a star graph is counter example. In a star graph, this is not a counter example, because in a star graph, A, B, C, D, E, F. In a star graph, this vertex has degree 5, and the minimum vertex cover is also this. So this is not a counter example. This is not a counter example. This is not a counter example. Actually, you can very easily create a counter example like this. So make a vertex, make a maximum degree vertex, and then just make sure that you don't get like you don't take this in the minimum vertex cover. Very simply, you can do this. Okay. So this is the idea. Two regular. Now, how can two regular be a counter example? How can two regular be a counter example? Basically, what should be the counter example for this statement? Can anyone tell me? The maximum degree vertex must be in minimum vertex cover. The counter example should be that there should be the maximum degree vertex which is not. Yes, yeah, two regular you can create. Like I can say some maximum degree vertex will not be there, but this is actually better example. I can say you can notice here the maximum degree vertex. There is only one maximum degree vertex, and that is not in our minimum vertex cover. So this is the idea. Tell me one thing. Now let's do the analysis of this. First, you tell me about edge cover. Let's do the analysis of edge cover. Now we will do the analysis of edge cover. What do you think? What is the size of edge cover? Like remember, edge cover exists. I told you edge. This is the first thing we know. Edge cover exists if and only if edge cover will exist. Edges which will cover vertices. Edge cover exists if and only if minimum degree should be greater than 0. Minimum degree should be greater than 0. I can say edge cover exists if and only if no isolated vertex. So you should not have any isolated vertices. Okay. Now let us assume there is no isolated vertex. Assume. Okay. Assume there is no isolated vertex. Assume the minimum degree is greater than or equal to greater than 0. This is the minimum degree. Then tell me, what can you say about beta dash? The size of minimum vertex cover. The size of minimum edge cover. The size of minimum edge cover. That means beta dash. What can you say about this beta dash? This size. What can you say? What observation you can make? This should definitely, what should it have? The size, this should definitely be greater than equal to what? N by 2. Yes or no? The size, this should be definitely greater than equal to N by 2 seal. Yes or no? Why? What is the reason? Because you can notice that one edge will cover how many vertices. The idea is very simple. Let's assume these are your vertices. Your vertices are A1, A2, A3, A4, A5, A6. And let us assume that the delta is greater than 0. It means minimum degree is means there is no isolated vertex. Now in this situation, tell me what will be the minimum edge cover. The minimum edge cover, what that will be? Means there is no isolated vertex. Then you can notice one edge will cover two vertices. Yes or no? Two vertices. Okay, if I take one edge, then two vertices will come. Yes or no? Two vertices will come if I take one edge. So these two vertices are gone. Then what I can do? Okay, then so these two edges will, but remember what I'm saying, that at least how many edges we need? One edge will give you two vertices. One edge will give you two vertices. One edge will give you. Okay, tell me. So minimum how many we need? Minimum how many we need to cover all the vertices? Minimum. So minimum we need 3. Yes or no? Yes or no? Minimum we need 3. Because one edge will give you two vertices. If I take one edge, E1, then it will give you two vertices. So minimum 3 we need. Two vertices, two vertices, two vertices. So at least, okay, there can be more. So remember, this beta dash, this should be greater than or equal to n by 2 seal. Can I say that beta dash is equal to n by 2? Can I say this is equal to n by 2 seal? Can I say this? That this is equal to n by 2 seal. This is equal to n by 2 seal. Tell me, can I do this? No, this is not correct. This is not correct. Because you can have this type of situation. So at least 3 edges we need. So in the minimum edge cover, at least 3 edges we need. At least 3 edges we need. But remember, it does not mean that 3 edges are enough. For example, consider this: A, B, C, D, E. Okay, F, G, H. In this, what is the size of edge cover? What is the beta dash? What is the beta dash? Means size of the edge cover. That will be 1, 2, 3, 4, 5, 6, 7. This will be 7. You have to take all the edges. In this question, you can notice you have to take all the edges. So you can notice beta dash is equal to 7, and this is not equal to. This is not equal to how many vertices you have. So you have two. I think so 5 total 8. 8 divided by 2. So beta dash is not equal to 8 divided by 2. Is this clear? So basically, the edge cover should be greater than this. Means minimum these many edges you need. Because one edge will give you two vertex. This one edge, this will give you two vertex. Another edge can give you two vertex minimum. These, okay, maybe more. But the point is minimum you need 3 edges. Yes or no? Is this clear? So at least 3 edges we need if you want to cover 6 vertices. The same thing you can do for example, 7. If you have 7 vertices, minimum how many edges we need? Minimum edge cover. So you can notice one edge will cover only 2 vertices. This will only cover 2 vertices. So if you want to cover all the 7 vertices, then you need at least 4 edges. E2, E3, E4. At least 4 you need. At least 4 you need. There can be more. There can be more. So at least 4 you need. I can say. At least 4 edges you need. At least 4 edges needed. This is only at least. Because there can be more. You may need more. Is this statement clear? Very simple statement. Size of minimum edge cover, that will be greater than or equal to n by 2 seal. But if this is equal to n by 2 seal, no. This is greater than or equal to n by 2 seal. Only this we can say. We cannot say this. Okay. What about this question? Is what about this? True or false? Does there exist a connected graph whose minimum vertex cover is V? Like, can you create a graph whose minimum vertex cover is V? What is the size of minimum vertex cover? Like in worst case. In worst case, what you can do? Tell me. Can you create a graph whose minimum vertex cover is V? Means all the vertices you have to take. Is it possible? This is my question. Is it possible that we have to take all the vertices? We have to take all the vertices in minimum, all the vertices in minimum vertex cover to cover all edges. Is this possible? Is this possible? This is not possible. This is not possible. See, don't say me. So don't say empty graph. What is the, for empty graph, what is beta? Tell me, for empty graph, what is beta? For empty graph, for this empty graph, what is beta? Beta means minimum vertex cover. What is beta for empty graph? That is 0. Array, that is 0. You don't have to take any vertex. You will cover all the edges. It exists. Like for example, A, B, C. This is your graph. Now for this graph, if you want to cover, if you want a vertex cover, this vertex cover is enough. You want to cover all the edges. How many security guard are needed? You want to cover all the edges. How many security guard are needed? How many security guard you need? 0. How many security guard you need? 0. So remember, there is a difference. Here you have 0. Don't say not exist. So vertex cover size will be 0. Actually, this is not exist. For example, if you have A, B, C, now tell me for this graph, the edge cover and vertex cover. Think about it. Vertex cover means how many security guard you need to cover all the edges. No security guard needed. So vertex cover will be this. Means beta will be 0. But edge cover does not exist. Edge cover does not exist because edge cover means edges which will cover all the vertices. You can notice this is covering all the edges. Yes or no? Can I say this is covering all the edges? Can I say this is covering all the edges? Yes, this is covering all the edges. This is covering all the edges. But you cannot do this. This is not covering all the vertices. We are not covering all the vertices here. So this is the difference. Edge cover does not exist. So for this graph, this will be 0. You don't need any security guard. So tell me, is it possible that all the vertices are in vertex cover? What about complete graph? What about this complete graph Kn? What is the vertex cover for the complete graph? For the complete graph, tell me, what will be the size of vertex cover? You have a complete graph. If you have a complete graph, is one vertex enough? Alok, is one vertex enough to cover all the edges? Can you cover all the edges by one vertex? Can you cover all the vertices, all the edges? Can you cover all the edges by one vertex? If I put one security guard here, can I cover all the edges? No, I cannot cover this edge because this is complete graph. Between every pair of vertices, there is edge. So what is the vertex cover? Minimum how many security guard you need here in this graph? In this graph, minimum how many security guard you need? Yes, n minus 1. Yes, n minus 1. 3, 2 is not enough. 2 is not enough because, see, why 2 is not enough? Tell me 2 is not enough. Why 2 is not enough? What is the reason 2 is not enough? 2 is not enough because if you take 2, like if you take 2 vertices, then the remaining 2 vertices will have edge. The remaining 2 vertices will have edge. Yes or no? Like let's assume you take 2 vertices. For example, let's assume you take A, comma B. These 2 vertices you take. Then this edge is not covered. This edge is not covered. Yes or no? This edge is not covered. So you need n minus 1. N minus 1 vertices you need. They will cover all the edges. These n minus 1 vertices will cover all the edges. So remember for Kn, because this is a complete graph. This is your complete graph on n vertices. You know, this is your complete graph on n vertices. So here, what is the vertex cover? Minimum vertex cover. You need n minus 1 vertices. Okay, tell me n minus 2 is, can I say n minus 2? For example, let's assume these are the vertices. Let's assume these are the vertices A1, A2, A3, an minus 1 and an. Now tell me this thing. Can I say n minus 2 vertices enough? Can I say these many vertices enough? N minus 2. These vertices, are they enough? Are they enough? Like if I take n minus 2 vertices, if I take n minus 2 vertices, are they enough? N minus 2 vertices, are they enough? The answer is no. Because if you take n minus 2 vertices, then the remaining, this edge will, who will cover? Who will cover this edge? If you take n minus 2 vertices, who will cover this edge? This edge is not covered. This edge is not covered. So n minus 1 vertices, no, n minus 2 vertices is not enough. What about n minus 1? Is that enough? N minus 1. N minus 1 vertices enough? Yes, these are enough. Yes. Because if you take n minus 1 vertices, now all the edges are covered. Is this clear? So in the worst case, remember, do you need all the vertices? Will you ever need all the vertices? Does there exist any graph for which you need all the vertices? You will never need all the vertices because n minus 1 vertices will do. In worst case, n minus 1 vertices will do. So the answer is no. Because in worst case, what you can do? Tell me. In worst case, n minus 1 vertices means v minus 1 vertices can cover all the edges. V minus 1 vertices can cover all edges. Yes or no? These many vertices, they will cover all the edges. Every edge will be covered. If you take v minus 1 vertices, every edge will be covered. Yes or no? So quite simple. So we have seen edge cover, vertex cover, these things we have seen. So the minimum number of edges in a edge cover, that is basically v by 2. This is the minimum number of edges in a edge cover. Okay. Tell me, yeah. So this, the covering number of a graph. So you have two covering number. There is vertex covering number. We write it as beta. This is the symbol for is beta, and the edge covering number, the symbol is beta dash. This is the edge covering number. Okay. So you know what is edge covering number. This is the size of minimum edge cover. This is the size of minimum edge cover. Edge cover. And this is the size of minimum vertex cover. You already know. So tell me, for these graphs, first question, for this cycle graph Cn, what is the beta and what is beta dash? What is beta and what is beta dash for cycle graph? What do you think? What is beta? Like this is your cycle graph. This is your cycle graph. This is your cycle graph. Then what is beta and what is beta dash? For this, what is beta? For this, how many vertices you need? If you want to cover all the edges, you need 2 vertices. Here also you need 2 vertices. These 2 vertices will do. These 2 vertices can cover all the edges. Here, these 2 vertices can cover all the edges. Okay, here, this vertex and this vertex, can they cover all the edges? No, they cannot cover all the edges. So here you need 3. And if you have 6, then you need 3. Here also you need 3. So what is beta? What should be the beta? Beta should be n by 2 seal. Beta should be n by 2 seal, right? This should be the beta, n by 2 seal. Because when you have 5 vertices, when you have C5, then you need 3 vertices. Okay, so this will be your beta. And what about beta dash? What about now beta dash? Beta dash. So what is beta dash for this graph? For these graphs, what is beta dash? Beta dash means edge cover. So how many edges you need? So for example, if your graph is this, if your graph is this, if your graph is this, then here, how many edges you need? If you take this edge, then for this actually, these 2 are enough. For this, you can take this edge, these 2 vertices are gone. Okay, these 2 vertices are gone. Next, if you take this edge, these 2 vertices are gone. So basically, and you can take one more edge. Similarly, here you can take these 2 edges. Here you can take this edge, this edge, this edge. So here you need 3, here you need 2, here you need 3. So what is the answer? The answer is the same. That will be n by 2 seal. Yes or no? Because remember, you already know this, we already know that beta dash is always greater than or equal to n by 2 seal. This we already know that beta dash is always greater than equal to, and for Cn this will be equal. For Cn this will be equal. Only this is enough. Only this is enough. Yes or no? For Cn. Is this clear? All these points, are they clear? Anyone has any doubt? Tell me, please tell me. Did you understand vertex cover, edge cover? Did you understand? We have taken many examples. Is it clear? Like, anyone has any doubt? Is there any statement did you which you did not understand? Did you understand this? Like, did you understand this, that beta, that the edge cover, the minimum edge cover is greater than or equal to n by 2 seal? Because one edge will cover only 2 vertices. You know, one edge can cover only 2 vertices. So if you want to cover all the vertices, at least these many edges are needed, at least, because one edge will cover only 2 vertices. 2 vertices are covered by one edge. So at least these many edges you need to cover all the vertices. So this is the analysis for Cn. What can you say about Pn? Path graph. What can you say about Pn? Tell me, what can you say about Pn? N is greater than or equal to, n is greater than or equal to 2. Because when n is equal to 1, then what is the problem? Tell me, when n is equal to 1, what is the problem? Edge cover is not defined. If you do n equal to 1, then edge cover will not be defined. This P1, this P1. So edge cover not defined, does not exist. So this is the idea. Now, so tell me what will be beta and what will be beta dash for these graphs. So for this graph, what will be beta? Vertex cover. So one is enough. One is enough. Here, this will be enough. Okay, next, what about this? You need 2. You need 2. You need 2. And here, what you need? Here you need 2. Again, you need 2. Yes or no? Here again, you need 2. These 2 are enough. And if you have 6, if you have 6, then if you have 6, then 1. Okay, this will cover these 2. So this will cover these 2, this will cover these 2. So finally you need 3. Here you need 3. And what about beta dash? Edge cover. Edge cover, what that will be? Here one edge is enough. Here 2 edges you have to take. Here you have to take how many edges? If you take this edge, so 2 edges you need to cover. You need to take. This edge you have to take, this edge you have to take. Then you have to take one more. This edge, this edge, this edge. So you have to take 3. So tell me what will be the answer? This is the idea. So for Pn where n is greater than or equal to 2, then what is beta? The beta is simply, I can say, n by 2 floor. The beta will be n by 2 floor and the beta dash will be n by 2 seal. The beta dash will be n by 2 seal. Yes or no? See, beta dash is already, you already know this you statement, you already know for all graph, beta dash is definitely greater than or equal to for all graph. This you already know for all graph. And for path graph, they will be equal. Is this clear? For path graph? Very simple. And what about this wheel graph? Wn. What about it? Wn. Wheel graph on n plus 1 vertices. For example, this is your W3. This is the W3. And this is your W4. So tell me, what is beta here? What is the beta here? Remember, this is your this is your K4 actually. This is your K4. So you need three vertices. This is K4. This is your W3. This is your W3, and this is same as K4. So this you need three vertices. And what is beta dash? For complete graph, what is beta? What is beta dash for complete graph? For complete graph, what is beta dash? Can anyone tell me? What is beta dash for complete graph? If you have Kn, then what will be beta dash? Beta dash means edge cover, minimum edge cover. What that will be? That will be n by 2 seal. That will be n by 2 seal. Because if you have Kn, then what you can do? Because you have Kn, like you have every two vertices. Remember, every two vertices are adjacent, right? Yes or no? This is your vertex set. Every two vertices are adjacent. So minimum edge cover will be like this. This minimum edge cover will work 1, 2, 3, 4, 5, 6, 7, 8, and so on and so on. So like this. So this will come because this is the edge, this is edge, this is edge. Between every two vertices you have edge. This is your complete graph. Between every two vertices you have edge. So you can take this edge, this edge, this edge, and so on. So finally, your size of minimum vertex cover, the size of minimum vertex cover will be n by 2 seal. Yes or no? That will be n by 2 seal. So like this you can do for Kn. So this will be the idea. Now tell me about this one, this Wn. So this beta dash, this here, because you have four vertices, so here it will be 2. 2 edges are enough. For example, you can take this edge, you can take this edge. Both will be covered. What about this? What about beta and what about beta dash here? Can you notice that beta dash? What will be the beta dash? This edge will cover these vertices. Okay. Or I can say that this edge will cover. So I think we will need 3. Yes, minimum. Yes, minimum edge cover. Yes, sorry for that. Minimum edge cover. That is minimum edge cover. Okay. So for this, because you have how many vertices you have? So here you have total 5 vertices. So beta dash actually will be 3. You only need 3. Because you can take this edge, you can take this edge, and then you can take to cover this, you can take this edge. And what will be beta? What will be beta? So this will cover all the edges. These edges will be covered by this. These edges will be covered by this, and plus the Cn, plus the Cn. For the Cn, what is needed? For the Cn, this n by 2 seal will be needed. Is this clear? Like what I'm saying? See, the beta, this will cover all these vertices. Okay, so this will, sorry, this will cover all the edges. And there is a Cn around you. This is the Cn, this is the Cn. For this Cn, you need n by 2 seal. For this Cn, you will need n by 2 seal. Correct? And the beta dash is total n by 2 seal. You only need n by 2 seal. Total 6 you have, so only 3 you need. You can take this. Okay, only 3 you need. So I hope you are getting this, because remember in Wn, if you have a Wn means you have a, there is a Cn. There is a Cn around you. There is a Cn around you. This is your Cn. And there is one vertex here. And there is one vertex here. So what will be beta? Minimum vertex cover. Beta means minimum vertex cover. So what will be your beta? You have to take this vertex. This middle vertex you have to take. This one is for this middle vertex. This middle vertex will cover all these edges. Now all these edges are done. Okay, remember all these edges will be gone. So all these edges will be covered by this A. These edges, they are covered by A. Okay, next, plus, now this Cn, you have a Cn around you. Now these edges are gone. All these edges we have covered. But these, what about these edges? What about these edges? These edges, what about these? So for them, you need n by 2 seal, right? This is for Cn. This is for the CN around A, around vertex A. Is this clear? How to get for wheel graph? The beta will be, this will be the beta. And beta dash is not a problem. Beta dash is not a problem because you have this vertex and there is a CN around you. This is the CN and this is your vertex. So here the beta dash will not be a problem. Beta dash means minimum edge cover. This will not be a problem because, okay, it will be just n by 2 seal. This will be enough, n by 2 seal. Because what you can do, around you, if you want to cover all the vertices, so what you can do, here you can take n by 2 floor and you can take +1. Okay, yes or no? So for example, here if you have odd, if you have C, if your n is odd, tell me, if your n is odd, then what you need to do? If your n is odd, if you have odd number of vertices here, then what you need to do? You can cover half of them, you can cover half of them, you can cover, and +1 you can cover like this, plus the remaining vertex you can cover like this. And if your n is even, then that will be simply n by 2. If this n is even, then what you can do? That will be simply n by 2 and +1. So ultimately in both the situation, you will get this. This is what you will get in both the situation. Is this point clear? Odd one, please repeat. See, if you have Wn here, if n is odd, then what will happen? For example, if your n is 5, then what will happen? If n is 5, means there is a C5 around you. There is a C5 around you, and there is a middle vertex. This is the middle vertex. Correct? Now you want beta dash. Means minimum edge cover. Minimum edge cover you want. Then what you need? Tell me what you will do. You want to cover all the vertices. If you want to cover all the vertices, you can take this. Now, if you take this, these will be covered. If you take this, these will be covered. Yes or no? These two vertices are covered. If you take this, these two vertices are covered. How many vertices are remaining? How many vertices are remaining? 2 vertices. Then you take this. Then these 2 vertices will be covered. So how many you need? Beta dash will be 3. Yes or no? Is this clear? If your n is odd, then what you can do? Basically, if your n is odd, then what you can say? From outside you can take. If your n is odd, then what you can do? From outside you can take n by 2 floor. From outside circle you can take n by 2 floor, and one edge you can take from here. One edge you can take from here. So that is same as n by 2 seal. Is this clear, Arpan? Tell me. Are you understanding these things or not? Let me know. See, very slowly I am teaching you all these things, like what we have to do. Like there is a, like for Wn, we have seen how to find vertex cover, how to find edge cover. Okay, the methods with examples. I am explaining all the concepts. Please let me know. Are you understanding or not? Do you have any doubt? Let me know. Okay, let's take 2 minutes, 3 minutes, 5 minutes. Please let me know if you have any doubt so far. So far, do you have any doubt? Is there anything that you did not understand so far? Any point, any single point that you did not understand? Any example, any point, any theorem, any result, any terminology, any concept? Is there anything that you did not understand so far? Some doubt is going on in your mind. Please let me know. Do you have any doubt? Okay, so remember, by default, the covering number of a graph, if I directly say covering number, then what it means? If I directly say covering number, what it means? It means vertex covering number. Remember, vertex covering number. So by default, if I directly say covering number of a graph, that means vertex covering number. This is the by default. Read this question and tell me which problem we are talking about here. Read this. Which problem are we talking about here? Let G be a graph whose vertex set represents the set of chemicals. Two vertices are adjacent if and only if they are compatible, means they react. Suppose we want to store a set of chemicals in different rooms. Naturally, we would like to store incompatible chemicals in different rooms. So which problem are we talking about here in this question? Independent set. Very good. Here actually we are talking about independent set, because what this question is saying, that there are some chemicals, like let's assume this chemical, they react. Let's assume these chemicals are reacting. Okay, so let's assume these are reacting, and let us assume that let's C2 is reacting with C4 and C2 is reacting with C5, and let us assume this is the scenario. Then what we want, so this is the scenario. G is a graph where vertex set is your set of chemicals. These are the chemicals. Two vertices are adjacent if and only if they react. If and only if they react. It simply means that they react. What this means? This means C1, C3 react. They react. Okay. Now the question is saying that what we want to do, we want to put reacting chemicals in a different room. Okay, what we want to do, we want to store I can say reacting chemicals. The chemicals will react. We want to store them in different rooms. So this is what we want to do. So what we need basically. So basically we need independent set. I cannot put them together. I cannot put them together. So I need independent set. So for example, I can put C1, C5, I can put together. This is fine. I can put them together. C1, C4, I can put together. This is fine. And what is the largest independent set? What is the largest independent set? Tell me. From here, only one chemical I can take. Only one chemical I can take from here. So actually the independence number, what that will be? Independence number will be 2. So this is the largest number of, 2 is the largest number of chemicals you can put together. These two you can put together, these two you can put together, these two you can put together. So here, which problem we are talking about? We are talking about independent set problem. So in the GATE exam, they can give you a problem and they will ask you like what we are talking about. They will give you something like this. And then they will ask you. Actually, this type of questions, they have come in the TIFR. In the TIFR exam, many times it will happen. They will give you a scenario and then they will ask you like, what are we talking about? Like, what is this problem? Is this vertex cover independent set? A is cover? What is this problem? Click. What is this problem? Okay. So that is the idea. So like this you can do. Okay. So one last thing we will do today. This is the last thing for today. This is the last topic, and that is the relation between vertex cover and independent set. And this is very interesting. We want to find the relation between vertex cover and independent set. Now tell me with example, let's try to understand this. Tell me if I have this example, A, B, C, D, E, F. So let's assume this is your example. Can anyone give me can anyone give me a vertex cover? Give me a vertex cover. Any vertex cover. Give me a vertex cover. Or maybe you can give me like, okay, what? So just give me a vertex cover. Whatever vertex cover you want, you can give me. Give me a vertex cover which will cover all the edges. So I can say, I can take this vertex cover. I can take A, B. Okay. I can take A, B, D. So I can take A, B, D, and F. A, B, D, F. So this is what I can take. Okay. This is your vertex cover. Now tell me very interesting thing. See, very interesting thing. Now you can notice the remaining vertices, what they will create. The remaining vertices, what they will create. Very interesting thing. The remaining vertices, what they will create. The remaining vertices means the complement, the remaining vertices. The remaining vertices means C, E. These are the, what they will create. They will create an independent set, right? Yes or no? They will create an independent set, correct? Are you getting my point? So this is the interesting thing. This is what I'm saying. So the remaining things will create an independent set. Now what I'm saying, this is the claim. This is the claim. If you have a vertex cover, okay, so let's assume you have a graph G, V, comma, E. This is your graph. This is your graph. Let us assume that S, which is subset of V, right? Let us assume S is a vertex cover. Let's assume this is vertex cover. If this is vertex cover, then the remaining vertices will create edge cover. Then what will happen? Then V minus S is independent set. Is independent set. Are you getting my point? So like here, this is the vertex cover. This is the vertex cover. And the remaining vertices, V minus S, this is S. So V minus S, that is your independent set. You can take, for example, you can take this vertex cover. Let's take this vertex cover S. What is this? Let me take this vertex cover. Like I can take B. If I take B, then these will be covered. Then I can take C. Okay, then I can take C. So this B comma C, they will cover. And then I can take E, F. This is also vertex cover. Yes or no? Is this vertex cover? B, C, F. Are we covering all the edges? Yes, we are covering all the edges. What? Okay, the remaining vertices S complement. What is the S complement? The remaining vertices means A comma BCF, right? BCF. So that will be ADE. This is what? This is independent set. Are you getting this point? This is independent set. This is interesting. So this is what I'm saying. If your vertex cover you have, then the complement will be independent set and vice versa. And vice versa. The same thing will happen if you have, for example, if S is independent set. If S is independent set, then what will be V minus S? If S is independent set, if S is independent set, then V minus S is vertex cover. Then that is a vertex cover. Then that will cover all the edges. V minus S will cover all the edges. And the proof is actually very cute proof. The proof is like this. See the very cute proof. What you do? Let's do this. So this is your graph, G, V, comma, E. This is your graph. And let us assume that S is vertex cover. Let us assume S is a subset of V. And let us assume this is your vertex cover. Let's assume this is the vertex cover. If this is the vertex cover, then what? Just look at this. Let's assume this is your V. This is your V. And this is your vertex cover. Let's assume this is your S. This part is S. So this part is basically S. Now this means this is a vertex cover, right? Remember, this is all the vertices. And what is this part? Can anyone tell me what is this part? This part is V minus S. Now notice that if this is your S, means if this is vertex cover. If this is vertex cover, is it possible that there is some edge here? Is it possible? Please tell me. If this is vertex cover, is it possible that there is some edge here? Is it possible? Why it is not possible? Why it is not possible? Like this edge, is it possible? Do we have any edge here? Why this is not possible? Because vertex cover should cover all the edges. This is vertex cover, so this should cover all the edges. This should cover all the edges. Yes or no? This should cover all edges. All edges must be covered by this. All edges. Every edge must be covered by this. But this edge is, so this is not possible. I can say this is not possible. There is no edge here. Yes or no? Because this vertex cover should cover all the edges. This should cover all the edges. So I can say this edge is not possible. In this area, there is no edge in this area. But this is fine, right? This is fine. Yes or no? Is this fine? Like one vertex here, one vertex here. This is fine. There is no problem. Okay, so this is fine. There is no problem here. But you cannot have this edge because this edge is not covered by the vertex cover. So this edge is not possible. Very simple point. So finally what I can say, if there is no edge here, so this is your vertex cover. I can say that this is your this is your vertex cover. Then what can I say about this area? Then what can I say about this area v minus s? These vertices, what can I say about these vertices? Are they adjacent or not? Are they non-adjacent? What can I say about these vertices? They are non-adjacent, right? These vertices are non-adjacent. These vertices, they are non-adjacent because they don't have edge. These vertices, they don't have edge. Yes or no? They cannot have edge. This type of edge can be there, no problem. This type of edge can be there. This type of thing can be there, no problem. All the edges are like this. All the edges are like this. But I can say that this area, look at this area. Look at these vertices. Look at these vertices. These vertices are not adjacent. Yes or no? These vertices are not adjacent. This edge cannot be there. So these area, these vertices, they are not adjacent. So this v minus s, this is a independent set. Did you understand this proof? Very simple, very cute proof. Yes or no? Like very simple proof. We are just using the definition. Just using the definition of vertex cover and using the definition of independent set. Very simple proof. So if this is your vertex cover, then this will be your independent set. The same thing, let me do for this. If this is independent set, so again you have a graph. In this graph this is your graph G, V, comma, E. Let us assume that, let us assume S. Okay, let's assume this is independent set. Let's assume this is independent set. So this S is independent set. This is the point. This area S. Now this is your independent set. These vertices are the independent set, means these vertices. Okay, these vertices are the independent set. And these vertices, what these vertices? These vertices are V minus S. Now tell me one thing. Tell me one thing. Do we have any edge here? Do we have any edge here? These vertices are independent set. So we don't have any edge here. So where are all the edges? Where are all the edges? Just ask this question. Where are all the edges? All the edges are like this. All the edges must be like this. Here you cannot have edge. This edge is not possible. This edge is not possible. Like this edge. Look at this edge. This edge is not possible because this is independent set. This area is the independent set. So this edge is not possible. So all the edges, where are all the edges? All the edges are like this. So what can I say about this area, V minus S area? Is it covering all the edges? Is this covering all the edges? This V minus S area, this area, this V minus S area, this is covering all the edges, right? This is covering all the edges. Is this clear? Because all the edges are like this. Where are all the edges? All the edges are like this. So all the edges are covered. This area is covering, this V minus S is covering all the edges because there is no edge here. We don't have any edge here because this is independent set. So I can say V minus S is the vertex cover. So I can say this will be the vertex cover. So this is what we have seen. We have seen that this is the node. What is the node? If you take any vertex cover, then the remaining vertices will be the edge independent set. See, this proof is like very cute proof, very simple proof. This proof, very simple. So this is the idea. If you have a graph G, if you have a graph G, V, comma, E, then what we are saying, then for this graph, I can say that if S is independent set, if S is independent set and S is subset of V, S must be subset because independent set I'm talking about. Okay, so if S is independent set, let S be subset of V. Now these are the 2 points. Or there is 1 point basically. S is independent set if and only if. S is independent set, then what it means? It means V minus S is what? Tell me, V minus S is what? That is vertex cover. And if this is vertex cover, then S will be independent set. So there is if and only if here. If S is independent set, then V minus S will be vertex cover. And if V minus S is vertex cover, then S will be independent set. Very simple. Or the same thing I can say like this. If S is vertex cover, then V minus S is independent set. And if V minus S is independent set, then S is vertex cover. Very simple. Okay. This proof, is this clear? Very simple proof. Let me ask you one more question. And this is very simple question. This is your graph G, V, comma E. And let us assume that S is a subset of V. So means you have set of vertices. This is your set of vertices. Now tell me, if you know S is vertex cover, S is a vertex cover. If you know S is a vertex cover, then what can you say about, if you know S is a vertex cover, this S is a vertex cover, then what can you say about beta? What can you say about beta? Beta means vertex cover number. What can you say about beta? And beta is vertex cover number. If you already know S is a vertex cover, this is one of the vertex cover, then what can you say about beta? Can I say beta is equal to cardinality of S? Can I say beta means minimum vertex cover, size of minimum vertex cover. That is your beta. Beta is size of minimum vertex cover. Size of minimum vertex cover. So if you know S is vertex cover, then what can you say about beta? This beta will definitely be less than equal to this. Yes or no? If this is already a vertex cover, then the minimum vertex cover will be less than this. S is already a vertex cover. So like in your hand, you have vertex cover. You already have a vertex cover in your hand. You already have this. Okay. So if you know that you have a vertex cover, then the minimum vertex cover should be less than this. Correct? Because this is minimum. So very simple. The same thing I can ask you for independent set. If you know that S is independent set, if you know this is independent set, then what can you say about alpha? What can you say about alpha? What can you say about alpha? Alpha means independence number. Means size of largest independent set. Tell me. If you already know that S is independent set, if you already know this, then the largest independent set should be greater than this. Yes or no? Greater than or equal to this. Agree? Because you already know that this is your independent set. This is independent set. So the largest independent set should be greater than or equal to this. Very simple point. These are simple points I'm asking. Okay, now let's see the relation between, now what we will see the relation between alpha comma beta. This relation we will see, where alpha is what? This is the largest independent, this is the independence number. This is the size of largest independent set. So this relation we need to see. Here, remember, this is your independence number. This is your independence number. Independence number means size of largest independent set. Largest. And you also know this beta. This is your size of, what is this? This is size of minimum vertex cover. This is the size of minimum vertex cover, or I can say this is your covering number, vertex covering number. Size of minimum vertex cover. Now let's see the relation between these two. So what will be that? Tell me one thing. If you know that this is your minimum, if you know this you already know. Let's assume that this is your largest vertex set. If this is your largest vertex set, this S, let's assume this is your this is your minimum vertex cover. Let us assume this is your minimum vertex cover. Let us assume. Then what can you say about V minus S? So this is your minimum vertex cover. S is your minimum vertex cover. Means the cardinality of S is what? Cardinality of S is what? Beta. Because I am assuming that S is minimum vertex cover. Then what can you say about V minus S? What can you say about V minus S? This is independent set. You can say that this is independent set. This is what you can say. You can say this is independent set, right? This V minus S is independent set. If this S is minimum vertex cover, ultimately this is a vertex cover, minimum or not. This is a vertex cover. S is a vertex cover. So V minus S is independent set. So the cardinality of S is beta. Then what can I say? This is your independent set. So tell me what will be alpha? The largest, this will be greater than equal to what? Remember, this is independent set. So the alpha should be greater than or equal to this. Yes or no? Are you getting my point? Because this is independent set. You have independent set in your hand. There is an independent set that you have. So the largest independent set that should be greater than this. That should be, I can say that should be n minus beta. Alpha should be greater than or equal to n minus beta, where n is number of vertices. N is the number of vertices. So alpha will be greater than or equal to n minus beta. Very simple. The same thing you tell me, if this is your largest independent set, if this is your largest independent set, this is your largest independent set, the cardinality of V is n. You have n vertices. So if this is your largest independent set, then what is the size of S? This is your largest independent set. Then what is the size of S? That is alpha. Size of S, that is your alpha. What can you say about V minus S? This V minus S, this is a vertex cover. This is a vertex cover. So if this is a vertex cover, then what should be the size of minimum vertex cover? What should be the size of minimum vertex cover? This is your vertex cover. So what should be the size of minimum vertex cover? That should be less than or equal to n minus alpha. That should be less than or equal to n minus alpha. Correct? So finally, we have two equations. These two equations we have. Alpha is greater than or equal to n minus 1 beta, and beta is less than equal to n minus 1 alpha. These two equations we have. From this equation, I can say alpha plus beta is greater than or equal to n. From this equation, I can say alpha plus beta is less than equal to n. Then from these two, what can I say? From these two, what can I say? I can say alpha plus beta is equal to n. I can say this is equal to n. Very simple. Did you understand this proof? See this, like using this diagram, you can very easily understand. Using this diagram, we are just using the definition. Nothing else we are doing. Only using the definition. Also, this is a final point. Just understand this. This is the final point. If S is largest independent set, if S is largest independent set, then what will be V minus S? You know, V minus S will be vertex cover. You know this. You know this will be vertex cover. But will this be minimum vertex cover? Will this be minimum vertex cover? Tell me. Will this be minimum vertex cover? You know that this will be vertex cover, but will this be minimum vertex cover? Will it be minimum vertex cover? Will it be minimum vertex cover? Yes, of course. Of course, it will be, because you know the equation. See, this is largest independent set. It means what? If this is largest independent set, it means what? This is equal to alpha. It means what? This is equal to alpha. Okay. This is equal to alpha. And you know, whatever is the minimum vertex cover, whatever is your minimum vertex cover. So what should be the size of minimum vertex cover? You just tell me this point. You just tell me this point. What will be size of minimum vertex cover? The size of minimum vertex cover should be n minus alpha. And what is the size of this V minus S? What is the size of V minus S? Size of V minus S is also n minus alpha. So yes, this is minimum vertex cover. No problem. Yes or no? Very simple point. See, S is largest independent set. It means the size of S is alpha. This is your largest independent set. Then the size of minimum vertex cover. The size of minimum vertex cover will be n minus 1 alpha, n minus alpha. this will be the size of minimum vertex cover. And this is a vertex cover v minus s. This is a vertex cover, and its size is also n minus alpha. So this is a minimum vertex cover. So this is a minimum vertex cover. Very simple. So anyway, this is the point that largest, if S is largest independent set, if S is largest independent set, then V minus S will be minimum vertex cover. This will be minimum vertex cover. And the same thing will happen two-way. This will happen. Vice versa. Okay. So this is your topic. So we have seen this topic very carefully. We have seen the complete analysis we have done. This proof, did you understand this proof? And this is a GATE exam question actually. Everything that we have seen in today's class, there is a GATE exam question on everything. In the past, when you solve the previous year GATE questions, then you will see this question is there in the previous GATE. And the proof is actually very simple. Using this diagram, like these type of diagrams I am creating to tell you the proof. Did you understand the proof? Please tell me. Did you understand the proof? Did you understand? So this is enough for today. Please let me know if anyone has any doubt. Don't keep any doubt. Whatever doubt you have, please ask. Whatever doubt, definition, example, theorem, proof, anything. Is there something that you did not understand? Is there something that is your doubt? Don't keep any doubt. Please ask. Please raise your hand and ask. Okay. Never keep any doubt. Whatever doubt you have asked. Hello, Arpan?
Yes, am I audible?
Yes.
So I had one doubt, which is in the wheel graph, when we are taking W5, so instead of calculating the outer cycle of 4 vertices and the plus one, doing the plus one, can we just take the number of vertices as 6 and then just use the n by 2 relation for calculating the minimum edge cover?
That's the same thing I told actually. If you notice, this is what I told. That for Wn, this is what I told, that the edge cover will be equal to, directly you can do n by 2 c.
Yes. So like
No, n by 2
basically
n
only
plus
taking the
1 by
number.
2 c, n plus 1 by 2 c. Okay, just wait. N by 2 seal will not work, because if you have 7 vertices, then if you have W7, then it should be 4. Like for example, if you have W4, yeah, so this is the correct, yeah, n by n plus 1 by 2. Yes. So I think this is what we have seen, I think, right?
Yes. Basically,
Uh,
taking the vertex and then
so let me just go back where we
yes.
were discussing this wheel graph. So this wheel graph we were discussing here. And for the wheel graph, what did I say? For the wheel graph, like, mm, if n is even, then what did I say? This is about beta dash. If n is even, then you can do n by 2 plus 1. There are n vertices around. So if n is even, then that will be n by 2. And there will be plus 1. This is not same as n by 2 seal. For example, if you have n equal to 4, then there will be 5 vertices in Wn. There will be 5 vertices in Wn. So actually this is not equal to, oh yeah, so this is correct. I think this will be, I think this will work. Will it work? If you have 5, then the answer, if you have 5, like you have this 5. Okay, so for this answer is coming to as 3. I think this will work, right? N plus 1 by 2. I think this will work. Yes or no? Nikhil, this will work n by n plus 1 by 2, because in Wn number of vertices, what is that? Number of vertices. What is number of vertices in Wn? Number of vertices, that is n plus 1. Okay, so the number of vertices is n plus 1. So now you can check that this n plus 1 by 2 will work, because for example, if your n is equal, like if you have w5, if you have w5, then there will be 6 vertices. Number of vertices will be 6, and you can notice you are getting 3. So number of vertices is n plus 1. So that will be yeah, this is correct. And if you have w4, if you have w4 means this is your w4. This is the w4. For this w4, the number of vertices will be 5. For this w4, what will be beta dash? What will be beta dash? You can take this as, it will cover these vertices. You can take this as, and you need to take one more as. So that will be actually 3. So if you take w4, then the answer actually should be number of vertices, number of 4 plus 1. This is the number of vertices divided by 2 seal. So I think this is correct. Yes, this will work. So actually, this is correct. So anyway, the point is that this you will have, because in Wn, number of vertices is n plus 1. So let me give you the conclusion. Let me give you the conclusion. So this n plus 1 seal, this will happen. Okay. So this is the final thing. Basically, in Wn, this is the confusion actually. Many times, even every, like I also get confused. This Wn, in this Wn, number of vertices is n plus 1. Remember, the number of vertices is n plus 1 in Wn. In Wn, this is the number of vertices. So the edge cover, the minimum edge cover will be equal to number of vertices divided by 2. Number of vertices divided by 2. So that will be number of vertices is n plus 1 divided by 2. This will be the answer. Yeah. Arpan, what is your doubt? Like, is it clear? Like, tell me, is your
So
doubt
in
clear?
the, for example, in the W4 wheel 4, so like we have a total set of, like when we see the diagram, we have a total set of vertices as 5. So can't
Yes.
we just do 5 plus 1 by 2? Because like the real number of vertices is 5. So 5 plus 1 by 2.
Yeah, that will not work when you have another number. Like, okay, so you can, like, you will have to do, for example, here you can notice, this is what you are saying. Actually, you are saying this. So see, but if you want one formula for every Wn, if you want one formula, this will be the one formula.
Okay.
Are you getting this point?
So basically, n's value we will take as Wn. From Wn, we'll take the n's value and then plus 1 by 2.
Yes, number of vertices in Wn is n plus 1. This is the number of vertices in Wn. That is n
Yes.
plus 1. So this is the conclusion. Wn
Yes.
has n plus 1 vertices. So beta dash will be n plus 1 by 2, because number of vertices is n plus 1. So this will be the beta dash. Okay.
Exactly.
And I think beta is correct. We have seen beta also. So is there any problem in beta?
So can you
Please tell
just
me.
this one? So basically, it's the same process, right? We just calculate the outer cycle and then do plus 1.
N by 2 seal for Cn. So if you have even number of people around you, then this will be plus 1. And if you have odd number of people around you, basically, we want to cover all the edges. We need to cover all the edges, right? So if you have even, then we have to do this. And if you have odd, then we have to cover all these edges, and we have to cover the outer edges. So that will depend on it. Yeah, this is correct. There is no problem here. This is absolutely correct. There is no problem.
So basically,
Arpan?
so if you have W4, then the VC will be just like floor of n by 2 plus 1.
Yes, for W4,
Yes.
this is your W4. You can just, like, you can just create. For example, this like in your copy, you can create this and you can check it. This is a very simple thing. This is your W4. This is the W4. In W4, you have 5 vertices. So what will be beta? Beta means minimum vertex cover. What will be minimum vertex cover? See, this you have to take to cover all these. So I
Yes.
can say A, B, C, D, E. Okay. So this I can say minimum vertex cover. If you notice the minimum vertex cover, that will be you have to take A so that you can cover all these edges. You have to take A to cover all these edges. Now you have to cover these outer edges. These outer edges you have to cover. So for that you can take E, B, comma E, so that you can cover all the outer edges. So anyway, the beta that will be basically because you have 5 edges. So beta will be like this. This middle vertex you have to take. This middle vertex you have to take
Yes.
plus the outer n is there. So there will be these many because this is for outer. This is for Cn around middle vertex. This is for shear around A. Okay, for that we need these many vertices we need if you want to cover that. So beta will be equal to 1 plus n by 2 seal. So here the answer will be 3. Is
Exactly.
this clear?
Exactly. Clear,
Any
sir.
other doubt, Arpan?
No, sir. Thank you very much, sir.
Okay. Hello, Nikhil?
Sir, am I audible?
Yes.
Sir, for the edge covering in the wheel graph n, like we had done previously, like the floor of n by 2 and then adding the one. Sir, isn't that the right approach?
Floor of n by 2, then
Plus
adding the
1.
1
Yes, sir.
in wheel graph. Like for example, if you take this, you are asking for vertex like beta, like edge cover you are asking, right?
Yes, sir. Beta dash.
Beta dash you are asking.
Yes, sir.
So basically you need to cover all the vertices.
Yeah.
So what is your approach here?
Sir,
Like in here,
I
let's
actually divided the wheel graph into two parts. One is cycle graph and then the central vertex. For the for the cycle, I took n by 2 seal because one edge will cover the two vertex.
right.
So like I just went to the lower figure up to which I can cover the two vertex, and then the central vertex and the remaining vertex I can attach if
So, okay, so
remaining.
basically your approach is like this. So you have Wn. In this Wn, this is your approach to find beta dash. This is your Cn.
Yes, sir.
This is your Cn, and like this you have. And to get beta dash, your approach is something like this. That C, if I want to cover this, then I will take plus 1. Like 1 edge I will take, right?
Uh, yes, sir.
And if I want to cover these outer edges, sorry, these outer vertices, because you are finding beta dash, means you want to cover vertices.
Yes, sir.
Minimum edge cover you want minimum edge cover. Minimum edge cover means you want to cover vertices.
Yes, sir.
You want to cover vertices. So to cover this vertex A, you are taking for A, you are taking 1 edge, right?
Yes, sir. Yes, sir.
And to cover these vertices, you are taking n by 2 seal.
No, no, floor.
But how can you take floor?
Sir, because the floor will give me like if I'm dividing by 2, that does mean like at the end I will be remaining with a single vertex. And the
Yes,
single vertex I can be like adding with the central vertex, so that will reduce my edge covering.
yes, that's correct. That's correct.
So we can
So
go with
actually
this
the
approach
answer is
too.
same. You can check this value. Okay, you can check, like you can check for n equal to even, n equal to odd. For n equal to n, even what this value will be, and for n equal to odd, which this value will be. So for example, if your n is even, then these will be same. Just take n equal to 4. N equal to 4, then the answer should be 3. If you
Yes,
take
sir.
n equal to 4, the answer should be 3. If you take n equal to 4.
Yes,
So
sir.
both of them are giving you 3.
Same
And
answer.
if you take n equal to, if you take n equal to 3, then the answer should be 3. If you take n equal to 3.
3, 1, 2, and
Okay.
then 3. Yes, sir.
So both are giving you, if you take n equal to 3, I think the lower part, this n plus 1 by 2, this is not giving the correct answer, right?
For n equal to
N equal to 3 if you take.
for n equal to 3, sir, I just let me go through it.
Then
Vertex
n
cover
equal to 3,
1,
3 by 2.
2, 3. Sir, it should be 3.
Yeah, this should be 2, sorry for that. So actually what I'm saying that, see, these two are basically same. If you take n equal to even, if n is even, then this value 1 plus n by 2 floor, this value will be equal to what? Because n is even, for example, you can take n equal to 8, then this value will be what? This value will be simply this value. This value will be simply what? This will be simply 5, correct? This value will be 5. And what about this value? N plus 1 by 2. What about this value? This
9
value
by
will be
2,
9 by
4,
2
5.
seal. So that is also 5.
Yes, sir.
And the same thing you do for n equal to odd. Like if you take n equal to odd, for example, if you take n equal to 9, then this value will be what?
5.
9 by 2. So 9 by 2 floor. So that will be 5. And if you take n equal to 9, if you
9,
take n
10,
equal to
5.
9, then this also will be 5. So both are actually same. This and this
Okay.
both are
Yes,
actually
sir.
same.
So for wheel graph of 3, what should be the edge covering?
Edge covering for the wheel graph, that should be 2.
Sir,
That should be
I
2.
not getting the 2.
Just take wheel graph.
Got. Sir, got it.
Just take wheel graph.
Got
This
it,
is
sir.
your wheel graph. Edge covering. We want to find edge covering. A, B, C, D. This is your wheel graph. Then we want to find edge covering, minimum edge covering. This is
Yes, sir, yes, sir.
minimum edge covering. So if you want minimum edge covering, then you can take this edge AB and CD.
Yes, sir, got it, sir.
This edge you can take and this edge you can take.
Yes, sir.
So
Got it.
that will be beta dash will be actually beta dash will be equal to 2.
And sir, for complete graph of Kn, the minimum vertex cover would be n minus 1, right?
Yes, because you cannot do with n minus 2, because if you have a complete graph, then it means between every two vertices there is edge. So you cannot leave two vertices. Like just think about it. If you leave two vertices, then between them there is a edge, and that edge who will cover?
We haven't counted. Yes, sir. Got it.
Correct?
Yes, sir. Got it, sir.
Any other doubt?
No, sir. All clear. Thank you.
Any other doubt, anyone? Anyone has any other doubt? See this, let me tell you one thing. This floor and seal, these things are confusing many times. Okay, this floor, seal, floor, seal. So just take n equal to even, n equal to odd. Whenever you see this type of situation, like there is some floor, there is some seal, this type of situation, if you see, just take n equal to even, n equal to odd, and that's it. Okay, so there is no need to confuse yourself. Just make two cases, n equal to even, n equal to odd. Okay. Okay, thank you everyone. See you tomorrow. Not tomorrow, actually. So in the evening we have digital logic class. Okay, in the evening.